Hello, welcome back to this lecture number 15 in our course on numerical analysis. We are studying the different divided differences, and we had seen how they can be treated as functions. And of course, we did not point out any application of such an approach. So let's go ahead and see what we will get if we decide you to see the divided differences as a function of a variable x. So this is what we are doing. We have f x naught comma dot 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 comma xn comma x. This is how we see the divided differences as a function of x. We remember we had defined even when the xi could be repeated, the value of the divided differences. And of course, if x is different from each of these xi's, then we know how to define the divided differences. So we have actually defined the divided differences where the last particular node can be any real number. And so we have a function, and the point of studying the divided differences by means of a function is the following. Whenever we have a function f from ab to r, and there are these nodes x naught up to xn, and suppose pn is the corresponding interpolating polynomial whose degree is less than or equal to n, then for any x, we have this formula. So remember, whenever you had Pn minus 1 and you wanted to look at Pn instead of f, if you had Pn, if instead of Pn you had Pn minus 1, then here we would have the corresponding divided difference. Or let's say that you have Pn plus 1. If you have an x, we call the x to be n plus 1, x n plus 1, which is, let's say, different from all the x naught up to xn. Then there is the polynomial Pn plus 1, which will interpolate the function f at the data x0, x1 up to xn plus 1. So the value at xn plus 1 will be given by the corresponding formula. And that we declare is also true whenever x also happens to be equal to one of the xi's. So this will need a proof, and as usual, we are not going to do too many proofs in this course. So this proof will be not taken up. But this is the formula which tells us that looking at divided differences as a function has this extra benefit that you can write down the error form in terms of the divided differences. Okay. So this was about divided differences. We have several applications already of this approach. We are now going to one further level of interpolating by polynomials. So suppose, let's again start afresh. We have a polynomial, we have a function f from a closed and bounded interval ab to real numbers, and it is continuously differentiable for any degree you want. So this r bigger than 0 means that you are allowing it to be differentiable for a high enough degree. What r is can be decided by our further discussion. Okay. Now there are these two theorems. So we have Taylor's theorem and we also have Lagrange's theorem. Taylor's theorem says that whenever you declare that you want a polynomial whose value at x naught, whose derivative's value at x naught, whose double derivative value at x naught, so on up to the mth derivative value at x naught should agree with the value of the function at x naught, the derivative of the function f at x naught, so on up to the mth derivative of the function f at x naught. If you are looking for a polynomial which at a fixed point has the property that the values of the function and the polynomial agree, the values of the first derivative of the function and the polynomial agree, and so on up to some certain number, say mth derivative. The value of the mth derivative of the function and the polynomial agree. If we demand such a thing, then there is the Taylor's polynomial, which gives the corresponding polynomial with that property. On the other hand, if you are taking the x0 up to xk and you are simply demanding the values of the function at these points be equal to values at these points for some polynomial, then you have the polynomial pk, which does the job. And now we become slightly bolder and we ask, can we ask for both these properties in a single polynomial? So can you ask, meaning we are asking that there should be a polynomial which has the value, which has the property that its different values on some points agree with the values of the function at those points, as well as at some certain derivatives the values agree. Now, when you are looking at x0 up to xk, you may not want the same bound of the derivative values on all these points. So you may want different values also, different possible derivatives also. So let's frame the question. We are starting with the function f, okay, and we have distinct nodes x0 up to xn in our interval AB. And now let's assume that for each node, some non-negative integer is prescribed. We call this mi. So mi can be 0, mi can be 1, 2, 5, 100, 2022, or any such number. Okay. Then is there a polynomial capital P with the property that for each I, the dk upon dxk of P at xi is the same as dk upon dxk of the function f, and where k goes from 0, 1, 2 up to mi. Is there such a polynomial? This is what we would want to ask, and the answer is, of course, there is such a thing. Such a polynomial is called the oscillating polynomial with the corresponding nodes ni and the non-negative integers mi. Okay, so the special cases of these is when you have n equal to 0, you have only x naught, and then there is a non-negative integer m naught. When you have such a situation, then we have the Taylor's theorem, which gives the answer. Whereas if you are looking at mi equal to 0 for all I, then we have Lagrange's theorem, which gives the answer. So Lagrange's theorem and Taylor's theorem, these are special cases of oscillating polynomials. So further, what we are going to do is that we are not studying this full theory of oscillating polynomials in general, but we are interested in the particular case of mi equal to 1 for all I. So our question would be that we have x0, x1 up to xn. We have n plus 1 distinct nodes. We want a polynomial p such that for the function f, the values of the function as well as the values of the derivative of the function agree with the corresponding values of the polynomial and the values of the derivative of the polynomial. This is what we are asking, and these are called Hermit polynomials. Now, in fact, the process given by Hermit can be generalized, and often the oscillating polynomials in general, they are called Hermit polynomials. But for us, Hermit polynomials are the ones where mi is equal to 1 for all I. We are not going to study the higher cases of mi. So we will not go in the general theory of oscillating polynomials. These are the Hermit polynomials for us. So what we are going to get is that given any function f on these n plus 1 nodes, the Hermit polynomial h2n plus 1 agrees with our function on each xi as well as with the f prime. So the derivative of the Hermit polynomial will agree with f prime on each xi. This is what we are going to do. The 2n plus 1 there says that the degree of the Hermit polynomial is at most 2n plus 1. You know, in the interpolating polynomials, whenever we had n plus 1 nodes, we had the polynomial of degree at most n, because a polynomial of degree at most n has n plus 1 coefficients. And whenever you are taking those n plus 1 conditions, you have information about n plus 1 coefficients, and therefore you get a polynomial of degree n, maximum up to n. Here we have n plus 1 conditions for the function values, n plus 1 conditions for the derivative, and therefore we have 2n plus 2 conditions, which will give you 2n plus 2 coefficients, and therefore the polynomial will have degree up to 2n plus 1. All right. So moreover, whenever you are looking at the graph of the function, then at those points x0 up to xn, the shape of the function, the graph of the function, and the shape of the graph of the Hermit polynomial, they are going to be the same. Because not just that the function values are same, the tangents are also the same. The derivative values are same, so the tangents are also the same. So the shape of the function is also equal to the shape of the corresponding polynomial near these points xi. Okay, so that is one very important observation, and we are now going to study the Hermit polynomials, their properties, their construction, and of course the corresponding errors. That's what we are going to do. We begin with our baby steps. Remember, whenever we have been given x0, x1 up to xn, we want to compute Hermit polynomials for mi equal to 1. If you have only x0 and you have m naught equal to 1, so you have the function value, you have the derivative at only one point, then Taylor's theorem comes and does the job. So the baby case for us will be when we have two nodes, x0 and x1, and we want to find the polynomial h, which has the property that at x0 and x1 the polynomial values and the function values agree, and further we also want that the agreement happens for the derivative at x0 and for the derivative at x1. This is what we are going to do. So let's reflect the case of the Lagrange polynomials, which we had studied not too long time back. We had studied it recently. So we had constructed what are called Lagrange polynomials for the nodes xi. So for that would mean that we had these polynomials Li, which had the property that on all the other xj, the value of Li was 0, and at xi the value was 1. So those were the properties of the Lagrange polynomials Li corresponding to each xi. You may think about this being a solution of a very special problem to the Lagrange interpolation problem, a very special case of the Lagrange interpolation problem. So here, in fact, we can have four special cases where our fx0 is 1, fx1 is 0, f prime x0 is 0, f prime x1 is 0. Then fx1 is 1, and the remaining three values, which are f of x0, f prime x0, and f prime x1, these are 0. And then two more such special cases by looking at f prime x0 and f prime x1 respectively. But here what we are going to do is that we should have we should have a polynomial which is 0 at some points and 1 at some other cases. So then immediately it should make us think about Lagrange polynomials. That the Lagrange polynomials should divide these functions. That is quite clear. Because if you are looking at h of x0 equal to f of x0 and h of x1 equal to f of x1, your polynomial should be a linear combination of Lagrange polynomials. But moreover, the corresponding derivative should be 0 at the points xi. So if you think more about it, you will realize that you should not have Li to be a factor, just Li, but you should have Li square as a factor, because when you have a square of Li as a factor of some polynomial, let's say your polynomial is something into Li square and you are computing the derivative, then the derivative of your polynomial will be something ka derivative into Li square plus something into Li square derivative. Now the Li square derivative has the property that it will be 2 Li prime into Li. There is an Li which still remains, and that's why on all the other xj's this polynomial will have value 0. So there are many properties that this Hermit polynomial should satisfy, and so we will bring them in step by step. But the very first property is that whenever you are looking at a particular hi, its value should be 0 on all other xj, and its derivative should also have value 0 on all other xj. Therefore, we realize that Li square has to be a factor. And now once again, if you go back to Lagrange interpolation, we had that Li should vanish on all other xj. Therefore, we had taken x minus xj as a factor of Li. And we then looked at what would happen at xi and we had to scale it carefully. Similarly, here once we have realized that li square has to be a factor, we should now scale it carefully, perhaps not just by a value, by a real number, but you may have to multiply by a polynomial. And that is what we need to do. So with the L0 and L1 being the corresponding Lagrange polynomials, we define hix to be 1 minus 2 x minus xi li prime at xi into li square at x. So once you realize that li square of x has to be a factor, then this remaining thing can be easily computed. So this scaling factor can be computed once you realize that li square has to be a factor for your Hermit polynomial. So these are the solutions to special problems. So we will call these also as Hermit polynomials. Let's compute the values of hi on xj. Li square of x being a factor of hix will tell you that on xj the value has to be 0. So hi of xj is delta xj. What is the value of hi on xi? This factor vanishes on xi because you have x minus xi sitting there. So on xi you get this highlighted factor vanishes, and so you have at xi hi is simply li square, and therefore it is the hi of xi is 1 square where it is 1. So hi xi is 1, hi xj is 0. And now we compute the derivative of hi prime on xj. In fact, this works out to be for any j, in particular for I. So you see that the computation of the derivative that is given here will give you that the value of this derivative is 0. So these hi for I equal to 0 and 1 have the property that h1, if you call them h0 and h1, h0 has the property that its value on x0 is 1 and its value on x1 is 0 and its derivatives on x0 and x1 are also 0. Similarly, h1 is the polynomial whose value is 1 on x1, whose value on x0 is 0 and whose derivatives are 0 on both x0 and x1. Okay, now we have to get a polynomial whose values on x0 and x1 are 0 but whose derivatives should have values 1 comma 0 and 0 comma 1. So we already know that li square should be divisible. Li square should be a factor of such a polynomial, but you want even the value on xi to be 0. So you will have to multiply by that linear factor x minus xi. And in fact, that is sufficient. We simply have hi hat x equal to x minus xi li square. Our definition of hi is slightly complicated, but the definition of hi hat, that is a bit simpler. And here if you compute the hi hat on xj0 for any j, because on I not equal to j, li square will give you 0, and I equal to j, this linear factor will give you 0. And if you want to compute the derivative, then you see that it is equal to delta ij. So we now have solved the very special cases, 4 special cases of our problem. And now it is clear that we have to take suitable linear combinations of h0, h1, h0 hat, and h1 hat. So we finally define this function h, the polynomial function h, to be f of x0, h0 plus f of x1, h1 plus f prime x0, h0 hat plus f prime x1, h1 hat. This is what we have, and of course you would note that the degree is less than or equal to 3. That is because the li have degree less equal 1 because you are looking at only 2 nodes, and their squares will have degree 2, and then you are multiplying by a certain linear factor in both the cases. The hi hat case is here right in front of our eyes, And if you were interested in looking at hi, you again see that li square will have degree less equal to, this is a polynomial of degree equal to 1 and all others are simply scalars. So the degree of our Hermit polynomial is now indeed less than or equal to 3. Our n is 1 because you are looking at x0 and x1, and the Hermit polynomial has degree less than or equal to 2 into 1 plus 1, which is 2 plus 1, which is 3. So this degree is less than or equal to 3. The general case is equally simpler. Once you have done this for the cases for our baby case, then you have to just define hi and hi hat in the similar way and take the corresponding linear combination. That is all that we have to do. So for general case, suppose you start with your function being defined on n plus 1 nodes, x0 up to xn, and you have the corresponding Lagrange polynomials L0 up to Ln. Then we have these Hermit polynomials hi for I equal to 0 up to n. Again, note that the degrees are correspondingly less than or equal to the corresponding things, because li square will have degree 2n, and here you have a linear factor, so hi has degree depending on what your L prime is. So this hi will have degree less than or equal to 2n plus 1, and there further we have that h. Okay, so let's just compute these values. Hi xj is delta ij. That is clear by looking at the value of the hi, and similarly we could compute hi prime at xj just as we had done in our baby case and get that this answer is 0. So this degree is less than or equal to 2n plus 1, and we have that hi hat xj, which is simply x minus xi li square. This has degree equal to 2n plus 1. So we again have that hi hat xj is 0 and hi hat prime at xj is going to be delta ij. And finally, we define that our Hermit polynomial h2n plus 1 of x, because it will have degree less than or equal to 2n plus 1, is simply summation f xi hi plus summation f prime at xi hi hat. Let's do an example. Until we do an example, things are not quite clear. The degree of this polynomial is indeed less than or equal to 2n plus 1. The degree might even be less depending on various these values. So we start with a very simple data. We have 3 points, we have 3 nodes, -1, 0 and 1. We have a function whose values are 2, 1 and 2 respectively on these 3 nodes. The derivative has values -8, 0 and 8 at these 3 nodes. So let's be careful. Our x0 will be -1, x1 will be 0 and x2 is 1. So n is 2, and so we should look at a polynomial of degree less than or equal to 5. 2 into 2 plus 1, 4 plus 1, 5. We should look at a polynomial of degree less than or equal to 5. Okay, so we are in fact going to get something of degree less than 5. We will see at the end. We should compute the Lagrange polynomials first. So we compute the Lagrange polynomials L0, L1 and L2. Let's verify that L0, let's compute the values of L0 on the x0, x1 and x2. x1 is 0 and you have already x here, so this value on x1 is 0 and your x2 is 1, so this linear factor x minus 1 will tell you that L0 of x1 is 0, L0 of x2 is 0, L0 of x0 is -1, so you get a -1 outside here and inside you will have -1 -1. So the product gives you 2 upon 2, which gives you 1. So indeed L0 is the Lagrange polynomial corresponding to our x0, which is -1. L1 is similarly, one can check, is the Lagrange polynomial for the given data, and L2 is the second Lagrange polynomial. So we have computed the 0th Lagrange polynomial, the first Lagrange polynomial and the second Lagrange polynomial. Once you have computed these, we are also going to need their derivatives. So let's write down the derivatives. These are the derivatives. This raw data is now computed. We have to now go and compute the H0, H1, H2, H0 hat, H1 hat, and H2 hat. These are the 6 polynomials that we need to compute. So we begin with H0. Remember the formula is 1 minus 2 x minus xi li prime at xi into the whole thing multiplied by li square. So this is what we have. And once you just compute various values, remember L0 prime at x0 would give you minus 3 by 2. X0 is minus 1. And the L0 prime is 1 by 2, 2x minus 1. So when you put minus 1 here, you get minus 2. Minus 1, that gives you minus 3. And so you have the derivative value at x0 to be minus 3 by 2. And your L0 square will become, L0 was 1 by 2 x into x minus 1. So the whole square is 1 by 4 x square x minus 1 whole square. When you simplify that out, you get 3x plus 4 into x square into x minus 1 whole square divided by 4. This inside 2 gets cancelled with this 2, this negative gets cancelled with this negative, and then you have the corresponding simplification. Similarly, h1x is 1 minus x square ka whole square, and h2x is minus 3x plus 4 into x square x plus 1 whole square divided by 4. These are the values of h0, h1 and h2. We compute the corresponding hats. They are simpler, so they can be computed in this following way. You have h0 hat to be x plus 1 x square x minus 1 whole square divided by 4. h1 hat is x into x 1 minus x square whole square, and h2 hat is x minus 1 x square x plus 1 whole square upon 4. So already you see that there are several common things that you can take. For instance, x square is a factor in h0, h2, h0 hat, h2 hat. Okay, already you have these things. Further, this h1 hat x will have to be multiplied by the derivative of the function at x1. Your x1 is equal to 0 and the derivative is also 0. So ideally we need not have computed h1 hat x, because the value by which you will multiply to h1 hat x is anyway 0. So that doesn't come really into the picture. Okay. So now we compute the final Hermit polynomial for the given data. So it will be summation f of xi hi plus the derivative value at xi into hi hat, and the value on x0 is given to be 2. This is h0 plus the value at x1 is given to be 1, and this is h1, and the value at x2 into h2. This is the first summation expanded. Then you have the second summation, which we have already observed will have only 2 terms. And then you sit down and do this. This is a delightful thing. I have done it myself. You know, this is a problem which I constructed myself by taking a particular polynomial of a slightly higher degree than 5 and computing its values and computing the values of the derivatives on these 3 points. And so we get the polynomial to be this polynomial: 3x power 4 minus 2x square plus 1. And of course, meaning you, whenever you have done these many calculations, you are never sure. You would want to check whether the values do turn out to be same. So we will quickly check that the value of this polynomial, this is an even polynomial. All the terms are of degree even. Therefore, at 1 and minus 1, it will have the same value. At 0, its value is 1, because you will just put x equal to 0 and you see that you get 1. At 1, the value is 3 minus 2 plus 1, which is 2, which is same as the value at minus 1. Compute its derivative, which is 12x cube minus 4x. And once again, you see that the value of the derivative at 0 is 0. The derivative value at minus 1 is minus 8. And the derivative value at 1 is indeed 8. So we do get the data we started with, and this is the polynomial. Degree is indeed less than or equal to 5. That is because it's an even polynomial. It cannot have any term of an odd degree. So luckily we did not have any x power 5 term. Where could it have come? This term could have come from this h term and this term, but here the coefficients cancel them out. And similarly, it could have come from here and here, but again the coefficients cancel them out. You see here you have -3, here you have 3, here you have -8, and here you have 8. So these degree 5 terms have cancelled each other, and good for us, because then we are left with a smaller degree polynomial. So we will now be looking at some more interesting properties of the Hermit polynomials from our next lecture. We stop at this moment and see you in the next lecture. Thank you.